Hi everyone. Today I'm going to talk about project 2B. A lot of you still are very confused about many aspects of this. I know this is a pretty late video to be making, but as you know, I was out traveling, and hopefully this would still be useful to many of you. So what I'm going to do is I'm going to talk you through the different aspects of the project, and I'm going to broadly talk about all the different things that you need to be doing in implementation to pass all the tests. So I'll particularly talk about things that are confusing a lot of different people. All right, so let's get started. First, what is it that we are actually asking you to do? We are saying that there are two kinds of processes in the system. There's reserved processes, which should get priority, and there are spot processes, which run when reserved processes are not running in the system, or when there's actually extra CPU cycles that reserved processes are not using. Okay, to give you an example, let's say there are three reserved processes using 60% each of the CPU. So there's 20% of the CPU that's free, and it's possible that a spot process will run using that 20%. Remember that the total amount of CPU available is 200% because we have two CPUs in x86. All right. So you should really read the lottery scheduler book if you want to understand how to do a lottery scheduler, how to implement a lottery scheduler, and the code for a lottery scheduler is really simple. If you look at Ramsey's book, he lays out the algorithm very clearly. You basically you basically generate a random number, and then you use that to figure out which process should run. Now there are a couple of tricky things here to note. So basically, people have the question of like, what should be the total number of tickets for which we should run, right? The total number of tickets should always be 200 because there will be I'm equating 1% of a CPU to one ticket. Okay, there are multiple ways to do this. You could say there are 1,000 tickets, and 5 tickets is equal to 1% of the CPU. That would also work. But in it's sort of the simple one way to do this, which I found very simple, is just to say one ticket represents 1% of the CPU, and if a process reserves 60%, it should get 60 tickets. So that's pretty simple. The second thing is, when you're running the lottery, it should always be over 200 tickets on each core. The thing to do is, only processes that are runnable, reserved processes that are runnable, should participate in the lottery. So in my previous example, let's say we had three processes, each with 60% reserved 60% of the CPU, right? So if all three processes are runnable, then the lottery, they would all participate in the lottery. Let's say the lottery brought out the ticket number 100, right? That means that the third process would run because the total number of tickets they have is 180. Sorry, the second process would run. The total number of tickets they have is 180, 60 for the first guy, 60 to 120 for the second guy, and 120 to 180 for the third guy. So if the random number picked is 100, the second guy would run. Okay. Now, if one of the processes is not runnable, right? It's doing I/O or something like that. Then in this case, you should hold the lottery only among the processes that are runnable. So we have three reserved processes. One of them is not runnable, and so we conduct a lottery among using um, only. Only the two reserved processes which are runnable participate in the lottery. So we'll have 0 to 60 for the first guy, and then 60 to 120 for the second guy. And then the rest would be spot processes. So the more reserved processes that are unable to run, the better the chance for a spot process to run, right? So in the example, let's say that we are conducting a lottery, and then we have two reserved processes that are able to run, and the random number that comes up is 150, right? Now in this case, what we should do is we should run a spot process, because 0 to 60 was the first reserved process, 60 to 120 was the second reserved process. So all the rest of it is just spot processes. So now what we want to do is we want to pick the spot process with the highest bid. Okay. And using this spot system call, you communicate that bid to the kernel. So the kernel looks at all the processes with like the highest bid and then selects one to run. Now you're free to do different things in here if several processes have the same bid. You can do round robin, you can do first in first out. As long as you do something reasonable, it should be fine. Okay. All right. So that's as to how you actually conduct the lottery. Okay. Another question people had is how do we know what process is reserved and what process is spot? Okay. So every process actually starts out as we sort of say here, every process defaults to being a spot instance with a bid of 0, which means that every process starts out as a spot process with a 0 bid. Okay. As they run, when they do the first reserve system call or bid spot system call, they can increase their bid or become a reserved process. In this project, we are actually building a mechanism to support all of these things, and we don't actually worry about policy. So don't worry about which process is reserved or which process is spot. If the process calls reserve or spot, you should handle it correctly. That's the thing that you should be worrying about. Don't worry about like which process is reserved and which process is spot. Okay. Um, so let's see. So let's talk about the 3 system calls that you guys should implement. Okay. So the 3 are very simple. Reserve just tells you what percent of the CPU is reserved for this process. There are a few checks that you should do before you implement this. Reserve should, of course, never be over 100%. It shouldn't be negative, and if you call reserve and there is not enough CPU cycles to support this reserve call, like for example, there are 3 reserved processes each with 60% of the CPU, and another process makes a reserve call for 60% of the CPU, you can't really support that because there's only 200%. So the reserve call should return -1, saying that I can't actually do this reservation. So we test all of these like sort of minor things in the tests. So please make sure that you do all of these things correctly. So let's see. So we have our spot system call, which I've already sort of talked about. So one thing people have been confused about is to when we say, for example, that when you beware of overflow and then you want to use a pair of integers. What we're saying is that like the charge is usually in nanodollars per millisecond, right? So what this means is if a reserved process has the rate of like 100 nanodollars per millisecond, that means that if it runs for 10 milliseconds, it's going to accumulate 1,000 nanodollars, right? So, and if we run for like 10 seconds, it's going to accumulate more. So it's very easy to accumulate so many nanodollars that you actually overflow the integer. Okay, so what we are asking you to do is to keep an integer for like microdollars, right? So one way to do this is to say every 10 power 6 nanodollars I'm going to store as 1 microdollar. So if you get large quantities of nanodollars, you can convert them into smaller number of microdollars, and so using this you can actually avoid overflow because you're storing a smaller number, right? Um, you can think of this similarly to saying instead of storing um, uh, all my money in terms of like dollars, I'm going to say how many $1,000 there are. Like if there's $2,000, I'm just going to store 2 because that indicates $2,000. So it's the same principle. Okay, let's see. What else do I want to talk about here? Oh yes. So in the pstat structure that you have, which is over here, um, in the pstat structure there is a charge field, okay, and that's microdollars. So if the charge is like so many microdollars plus so many nanodollars, don't worry about the nanodollar part. Okay, we are not actually checking whether the nanodollar part is correct. So just return how many microdollars have been processed, and that's what all our tests do. We run until at least 1 microdollar charge has been accumulated, then we check that you're returning that correctly. So in this particular field, you just have to worry about like about microdollars. Note that this does not mean that you can only store microdollars in an implementation, right? You, the the process may incur charges in nanodollars, but over time it can accumulate and then become a microdollar. So you actually do need to store both. Okay. So that's about overflow, about what you should return in pstat, and all the three system calls. Okay. So now I'm actually going to talk to you about like how you would implement this stuff. So let's go look at some code. Okay. So here we are. Um, so for implementing the system call, let's just go in here. I'll show you what I need to do. Okay. Hmm. My copy seems to be corrupt for some reason. Yes, please overwrite. And here we are. And let's remove this CSX. Oh, no, okay. Ah, now I understand what's going on. Sorry, minor confusion. Anyway, so we are in this new copy that we have here. All right. So the first thing you need to do is you need to add these three system calls. Now this should be relatively easy for you because you've already done P1B and you know how to do a system call, right? So get PID, I star. So you know all the places where you should add a system call, and then you would just like do a similar thing for reserve, spot, and get p info. So that part should be relatively straightforward for you by now. Okay, so we're not going to talk too much about like how you would do that. Let's see. Oh yes. So what do you actually do when you get a percent or a spot for or a bid for a spot process, right? And my recommendation sort of is to sort of go into the process structure, right? And so this is already storing a lot of information per process. Okay. So my recommendation is to just sort of modify this so that you're adding new things into the structure. So here you could say you could add fields to say I'm going to store let's say let's just add here, so you can say this is going to be my reservation percent. You can say this is going to be my spot bid. You could say this is going to be my charge, and so on and so forth. So it's totally okay to change the process structure. Don't feel that you should only change structures that you yourself have written. That's fine. You can actually change the process structure. In fact, that's what we recommend for this particular project. So your process structure is now actually going to hold all these different values that you are passing in through the system call, right? You'll be passing in the reservation percent, the spot bid, and the charge. Now note that we actually need to store other things too, right? So the PSAT structure asks us to collect information about all the different processes, and it asks us for different information like the in use thing, whether the slot of the process table is in use. Now this is easy to find because there's a state associated with each process, right? This will tell you whether it's in unused, an embryo, sleeping, runnable, running, or zombie. So you can use this to figure out whether it's in use or not. I'll leave that up to you. It also asks us about the PID of each process, which is already in there. Number of times it's been chosen. So this is another thing that you will have to include in the structure. That number of milliseconds the process has run, and the charge which already we put in here. So all of these fields you add into the process structure. Okay, and when you actually get the p info system call, what you do is you use the p table. I'm not sure if you guys, you guys should already be knowing about the p table. So the p table is actually holding all of the different processes in the system, right? So that's what we're currently using the p table for. So you should just go through the p table, and then like for each, so that will give you pointers to all the different processes in the system, right? Because we have an array of processes. For each process, check all of these different fields and then populate them into the pstat and then just return it. Okay. So that is all your get pinfo call is supposed to do. It's supposed to be very simple. It's just like a read of a file. Um, so one thing people have been getting confused about is how do I actually get this information, which will be in kernel.proc all the way to kernel sysproc.c, um, right? So this is where you will actually be defining your new system calls, and then um, how do I actually access p table in here, because it's a global variable in the proc file. Okay, an easy way to do this is to have functions in here like sys underscore spot or sys underscore reserve in your sysproc file, and then have them call functions in the proc file. So define a new function here, which will sorry um, define a new function in here which will say fill a pstat structure. Okay, so this should be relatively easy to do, or which will set fill a pstat structure, right? So then what you can do is you can have uh, sorry about that. You could have a call like sys get pinfo void. You should use arg pointer to actually get the memory for the pointer, and then what you do is you just call in a function saying fill pstat or whatever, and then you pass p to that, and that will be in here. So this will be a void function or maybe an int function, because you might get a null pointer. So here you would actually use the read p table, um, and then fill pstat. Okay, so that's basically how you would do this, right? So have functions internal to proc which deal with the process table, which actually acquire and release the lock and so on and so forth, and then just pass on the values back to back via the return value of the function, and then in sys underscore get p info, use that to actually make the system call work. Okay, so this would be sort of like clean separation, because sysproc doesn't know about ptable or the lock or anything like that. That's all in proc.c, but then that is used in order to implement sys underscore get p info. Okay, so I think that should be the most complex thing that you need to do these three calls. Reserve and spot should be extremely easy. If you look at here, we already have we are already accessing the proc variable in here, so you don't need to do much to actually access the current process. You just need to set the field of the current process in spot or reserve. So one thing to note is that the same process may call reserve and spot. Okay, which means that you need to be able to tell whether a process which is previously a reserved process is now a spot process or vice versa. The way I did this in my implementation is, if the reservation percent for a process is 0, then it's a spot process. Okay, so when you get a spot system call, not only do you have to set the bid value for the spot, you also need to reset the reservation percent, because it might have been previously set. You also need to do this in the reverse order if it was previously a spot process and now gets a reserve call. Okay, so that's something to keep in mind. Okay. Oh, and remember that we say you can actually build a variant of the PS um, program using getPinfo. So let me just quickly show you how we did that. Okay. So it's actually pretty simple, right? So all you do is you declare a pstat struct, you get pinfo that, and then once you have that, you just like run through the different processes, see if they're in use, and if they're in use, you print out all the statistics for the process. So it's a very simple way to like get to the state of the system. Okay, so you might be doing something like this for your own internal debugging, but we do not actually require you to do this. All right. So if you have done everything that I've said so far, you now have the three system calls: the reserve, the spot, and the get pin for system call. So you can actually use it to tell for processes to tell the kernel that they're either reserve or spot processes, and you can use the get pin for call to see what's actually going on in the system. Okay. Now you have to implement the actual tricky part, which is the lottery scheduler. But it's actually really simple. Um, remember that we are holding a separate a lottery per kernel. Okay. Um, so now we have the restriction in XV6 that a process can only run on one processor. Okay. This actually makes things really simple for you. So if a process is running on one core, it'll be it'll be in the running state. So it will not actually be in the runnable state when you look for it on the other core. Okay. You don't need to run a lottery for that process. You just like ignore that process in your lottery entirely. That's basically what you do. Okay. So so people have been asking though, like how do we choose what process to run, and like how do we run different lotteries. So let me show you how to do that. So so this code is a per CPU process scheduler. That's what it says up on top, if you can read this. Okay. What this means is that this code is executed by each CPU in your system. Okay. So um, what this means for you is that the way to do a lottery for each CPU has already been sort of set up for you. You don't need to do anything to run it on each CPU. That's already been done for you. Scheduler already does most of the work. It acquires the p-table lock so that the CPUs don't stomp on each other. So one CPU will be checking the process table and then running a process at one time. So all you really have to do is that you have to run the lottery inside the scheduler. Okay, right now it's doing a round robin in order to pick a process. All you have to do is just run a lottery in this part of the code, pick a process, and then let the scheduler do its thing, right? So don't worry about like how do I switch CPUs, or how do I make it so that I run it on both CPUs. That's all been already done for you. All you really need to do is in this part of the code, look at what is in ptable, run a lottery with all the reserved runnable processes. If the ticket that's picked is not in any of, is not one of the tickets of the runnable reserved processes, pick a spot process. Pick the spot process with the highest bid. If there are many among that, use round robin or FIFO. Then pick that process and then return it here, and then the rest of the code just works. You just switch switch EVM using the process, mark it as running, and then you switch and you come back. So all of this just works. Just picking the it's only picking the process that is different, and for that you have to run the lottery. Okay. Again, to sort of reiterate, a very simple way you can do this is run the lottery with 200 tickets, one ticket for each percent of the CPU. When a process calls reserved with X, give it X tickets. Among the reserved processes that are runnable, um, uh, okay, I've been using this term lately and then you might have been confused. So, okay, so what do I mean when I say run the lottery only among the processes which are runnable, right? What I mean is, um, when you're running the lottery, you basically you say there are total of 200 tickets in the system, and then so many tickets are going to be for each reserved process. Okay, if there are 200 tickets, and if there's a reserved process with 60% reservation, then tickets 0 to 60 would go for that first process. Okay, now if this process was not runnable, we would not allocate these tickets for this process. If there are no reserved process, all of it would go to spot processes. That's basically what I mean when I say um, a process participates in the lottery. It gets some amount of the 200 tickets allocated to it based on its reservation percent. That's what it means. Okay, so your algorithm should be really simple. Um, Generate a random number. See whether it's a reserved process. If it's a reserved process, just pick it and run it, and you're done. If it's not, you should run a spot process. For a spot process, pick this process with the highest bid. There are many with this same bid. Choose among them in any way you want. You can do first in, first out. You can do FIFO, whatever it is that you want. In my implementation, I just look at how many times the processes have run, because we have a field called a number of times chosen, right, in our process structure. So I just pick the process that's been run the least amount of time, so that there is some notion of fairness. Okay. So I think that should be it. Um, let's see. Okay. So let me talk about the tests for a little bit, right? Because tests have been released and some people have been failing on these tests and they've been getting freaked out. So let's see. So the build test that's being performed actually does more than just build your code. Okay, so it will build your code. If it doesn't build, it's going to fail. Then it's going to check for whether you have the three system calls. Okay, it will check whether you have spot, whether you have reserve, whether you have get p info. If you don't have that, the build will fail. Now it also checks for the structure of pstat. Okay, so if you've changed the pstat structure, it will fail. So all of the fields that we have given here, let's see, given here, should actually be in pstat in your code. You can add additional fields, that's not going to affect us, but we do check that you have all these fields. So if you've changed the names of these fields or you've deleted one of these fields, then your code is going to fail to build. Okay, so you could fail to build because of all of these fields, not because you run make and then it fails. Okay, so build is a sort of a complicated test case. So make sure that you do that correctly. Also, the way we are testing that your code doesn't do the correct thing is by we will give your code some input, and then we will keep checking the output for a long time to see whether your code actually produces the correct output. The reason we do this is sometimes your code slows down for no fault of yours, and there may be other people in the system or whatever, but we don't want to penalize you for that. So as long as your code produces the correct output, even if it's like after some delay, your test should still pass. Okay. As a side effect of this, even if your code produces the wrong thing, we don't actually immediately tell you it's wrong. We keep waiting. Okay, we keep waiting, and then after some amount of time, let's say 30 seconds, we see that you haven't produced the correct output, and then we fail the test. So that's why whenever you're failing any test, it will always show as a timeout failure. Okay, it doesn't mean there's an infinite loop in your code. It means that you're actually failing the test. So I think that should be about everything that you require to do P2B successfully. So good luck and send us your other questions.